right. Welcome everyone to day 2 of Understanding Latency 3.0. My name is Björn Iverteigen Moncler and I will be your host. We had a great session yesterday and I think we have a great session for you today as well. And there was a lot of questions yesterday about whether we will record this and whether the slides will be available and stuff like that. Yes, they will. We will be posting the recordings on YouTube, and the slides will also be made available in a Google Drive folder or something like that. So if you missed a detail somewhere, don't despair. You can go back and look at the recording and find the slides after the event, and we'll email that to everyone. Yeah, it should be easy to find once it's online. The agenda for today is we're starting out off with Dave Todd talking about eliminating latency issues with LibreQOS. Then Greg White will be talking about this sequence of abbreviations. So that is non-queue building per hop behavior and DSCP, which I don't even want to expand. Then Stuart Cheshire will be talking about intelligent source buffer management to minimize total network latency. Neil Cardwell will be talking about how BBR congestion control tackles latency. Then we'll have a short break. And after the break, Christian Anderson from Ericsson will talk about 5G and latency explained. And then Simon Sundberg will finish off this session with measuring network latency from a wireless ISP, variations within and across subnets. So that is the plan for this evening. And I think we'll just kick it off. If you're ready, Dave, you can share your screen and get started.
You have to allow me to start video. Yeah. There we go.
There we go. Everybody. I can see you now.
All right. Let me, yes, I want to share my screen. Chrome tab. Oh, there. And
for those of you who don't know Dave, he's Chief Science Officer at LibreQOS and has been active with the Buffer Builder project for many years. Developed FQ Coddle and Cake, and generally providing solutions for improving latency in various network equipment.
All right. Am I still with you guys? Do I exist?
You are. We can see your slides too.
All right. That's good. Let's switch to this. Forgive me, I'm not particularly good at Zoom. There we go. So what I see, I don't see my slides at all right now, guys. I just see a blank screen.
We saw your slides there for a little while. Then we saw a YouTube screen, and then we saw the slides again.
Huh. Okay, try it again.
Now I can see your slides. The slide.
All I still see is nothing. So if you're seeing Understanding Latency 3.0 slide with some things.
Yeah, now you're moving to the next slide. Now you're on the title slide.
All right. Well, I'm not picking it up on my system at all, so I'll just fake it, okay? One of the things that we struggle with is actually representing what QoE issues mean to the operator so that they can detect them and find them before the user actually sees them. And we work on trying to find useful graphs and videos to help the operator do that. One of the cool things we did recently is we've got a way of looking at latency to various and sundry CDNs. And you can delve deep into what's going on when you see that. So LibreQOS leverages Rust, C, Python, eBPF, and Cake to give an operator the ability to successfully manage their bandwidth for all their subscribers. The core engine of it is open source, Anybody can use it, and there's over 300 ISPs using it today. And you can fit about 30,000 subscribers onto a very inexpensive box. In the field, we don't see much of that. We see a lot more people focus much more closely to the edge of their network, so it's typically 5 to 10,000 tops. We're in 28 states and 60 countries now. So after working on buffer bloat for so long, I've come to really believe that fair queuing, flow queuing, in our case, packet shaping and AQMs, completely remove all issues with latency on an ISP network. There's a free demo available. But once you have that thing going, looking at what's operationally a problem is useful. So the most popular feature we currently have, again, I do not see my own slides at all, so I'm assuming that we're at the Sankey Total Network Overview. Yes?
That's correct, yes.
All right. Is we can model a network up to 8 hops deep. There's a lot of towers involved in the WISP thing, so we can see where latency is occurring at a very detailed level and be able to manage the bandwidth to each of those things. Now, when people first run Libre QoS, they don't have all green. They're typically a sea of red. And you can see here that the uppermost tower here has a bit of a bandwidth problem to it. The remaining customers below are doing okay. We see people just leave this enormous sand key for all of their towers just up all the time on a big display. We can drill down into trying to represent what the bandwidth and latency issues are at almost any level. And you can see a histogram in this case, for example, of the latency to a given node, and a heat map describing what's going on for the rest of their network. Recently, we started taking apart the latency problem outside of the ISP network. In this particular case, we're seeing Fastly was transmitting an awful lot of data on a given day to a given set of subscribers, and it was transmitting so much that the red lines there indicate those are TCP retransmits happening. So they are flooding the network with some kind of data. But it's good to know and look at and say, well, maybe there's an issue with trying to get an IXP involved or some other way of sharing bandwidth. We use a lot of test tools that haven't been talked about here. Flint is the big one. iPerf2 is pretty popular with us. The new Crusader tool is really cool, and I hope that more people try using that to analyze what's going on the network. There's a really neat new tool for looking at what's going on inside containers called XTCP2. Network quality, everyone hopefully knows what that one is. And all the speed tests have buffer bloat metrics now. The most common test that we use is the waveform test. Recently added the ability to track TCP transmits to the overall forwarding engine. In this particular case, we can see this enormous lump in what happened here for TCP retransmits, and not much improvement or increase in the bandwidth. What had actually happened here is that the operator had left a sniffer on a given segment of their network, which was dropping packets like mad. So it was able to easily look at the logs and say, aha, this is what I did wrong, and then go fix it. Looking at, well, TCP, we'll miss it when it's gone. We've experimented with AI a lot. We use Copilot and ChatGPT. With careful supervision, it helps. You can also dig some really deep holes with it. And given all the level of data that we're able to collect from the ISP viewpoint, we fed a lot of it to various LLMs, but operational usefulness has so far eluded us. This picture here is what ChatGPT thought would be a useful graph of mapping what your bandwidth and performance look like. So a big thing that people don't seem to get is that 98% of flows don't need AQM, but the 2% need it desperately, and the 98% need it 2% well taken care of. The other big thing in the ISP world is that the only major driver for subscriber bandwidth need is video streaming. If you want 4K video, you need to provision about 35 megabits to the user, and most people are actually quite happy with much lower and a lower thing there. Again, once you have flow queuing, all the basic low latency things that people need and require issues, those vanish. Gaming, DNS, keystrokes, VoIP, and video conferencing always just work. And once you put cake on the upload, nobody really cares about lag anymore. Despite us using a middle box, we certainly do recommend you have good Wi-Fi at the other side of the connection. Above 100 megabits, a lot of the buffer bloat starts moving to the Wi-Fi. Just yesterday, we had one of our users paste this graph and tell us this little story. Uh, they were downloading a whole bunch of stuff to their Xbox, but the rest of the network was pretty good. They were just complaining as to why the download was taking so long. And the ISP offered the 50 megabit plan and then explained that they were running software that kept the interactivity up. And she responded with, "You guys are the best internet we ever had." We get a lot of that from almost all of our customers. So I've been working on LibreQOS now for about 3 years. It leverages the latest and greatest things from the Linux kernel for eBPF and Cake. Recently added support for some other statistics that are useful. NetFlow, we can now route around stuff using ISIS. There's a whole bunch of integration with ISPs, CRMs. The Splunk, UISP, and Sonar and PowerCode are basically done. There's Gaia, Wispgate, and Visp still in progress. The extensive flow tracking, being able to see what's going on in and outside of your network. And we managed to cut the memory use down. And in a typical environment, this is the test on the right here. You can see the min to the max latency is about 50% difference, which is a lot better than what anybody else can do today. And that's really it. We are operational. We deployed. It's done. The whole issue with almost everything going on. And by the way, for the next speaker, we support NQB already. We're not seeing any in the field. Thanks very much.
Right. Thank you, Dave. Very interesting stuff. Do we have questions in the chat? Let me see. I don't see any questions in the chat. Let me check the Q&A tool. All right. So Saidira is asking, Dave, you mentioned yesterday about peeping kind of tools. Where do
Ah,
you use them? What do you measure? Node processing times, hop latencies?
my camera's over here. My screen's over here. Everything that we do is passive metrics, and a great deal of it comes from a highly modified version of the EP-ping tool. We pull out all the round trip time statistics that we use for measurements using it, and we've made the advancements to that open source.
All right.
Oh, I see the question for LibreQOS used with a satellite. Yes, um, but we had a lot of contact with the Starlink folk. They went their own way, but they are using FQCoddle on the Wi-Fi and a Coddle-like AQM on their downlinks.
Another question here is, and how do they work well along with the chipset hardware accelerators?
That's a big question. So in the case of LibreQOS, we're a middle box, and we don't really need to worry about what's on the CPU all that much, although it does help. In most cases today, if you turn off the hardware acceleration, you can get better latency. You'll see, for example, I'm a big fan of the MT79 chipset. I could probably post the link here. The factory drivers have over a second of latency under load at a fairly short distance. So what we're doing today in OpenWRT is about 60. Um, I don't know what the right answer is. We see a lot of, we've seen several offloads of FQCoddle to various forms, some forms of CPE. And for users that really care about it, turning off acceleration gives them better performance. So pick your poison.
Right. And then Dave is asking, how much performance impact was there when you guys added the TCP retransmit detection? I assume it was slightly expensive.
Slightly expensive. Actually, no. It was, compared to everything else, it was really trivial. A typical box that we have today can easily push 50 gigabits, and doing the additional work to do leveraging AI is just something that can else use up to the CPU. But the code's in there, you can try it.
All right. Great questions. If there are more questions, I hope David will stick around for a while.
There's a
Um,
bunch of us here.
our
All right,
next,
thank you very much for having me.
thank you very much. Our next speaker is Greg White from Cable Labs, where he's a distinguished technologist, and he'll be talking about the non-queue building per hop behavior and DSCP, which is a recent RFC from the IETF. So, Greg, please, the stage is yours.
Right, thank you. And oops, hold on 1 second while I get my
I can hear you well and see you well.
great. Hopefully you'll see my slides well here in just a second.
Now I can see your slides as well.
Excellent. And yeah, we're not quite to RFC yet with the NQB technology, but we're getting very close. And so um, uh, I thought this would be a good opportunity to introduce folks if they have not been introduced to the NQB concept in the past. And for those who are familiar with it, an update on the status, kind of where we've ended up in the IETF through that standardization process. Um, and also start off with a little bit of the history, kind of where, how this work got started and some of the motivations for it. So. Thank you for inviting me to this as well, Bjorn and Domos. Appreciate the opportunity. All right. So what is NQB? A little bit of the history and the background. So it really kind of starts with the question at the top of the slide. Can we allow low data rate, latency sensitive applications to avoid all of the latency and jitter and packet loss that's caused by bulk traffic? I'm assuming everyone on the call is familiar at this point with buffer bloat and the impact that congestion control, classical congestion control has on latency of other traffic, of itself and other traffic when it shares a network queue. Um, and we're very interested in ways to resolve that issue, and starting off with active queue management and looking at things like FQCODL and then currently looking at L4S as a solution to this. But there's this class of traffic which is low data rate and very latency sensitive, and we'd like to be able to make sure that that gets good performance through a network as well. So there have been some previous attempts at this over the years. You're going back to the earliest days of the internet, the idea of identifying the latency sensitive traffic and prioritizing it in the network is has been implemented. A vast majority of network equipment supports priority queues. And it's a simple matter of identifying the worthy traffic and getting into that higher priority queue, problem solved, right? Works great in theory, not so great in practice across the internet end to end. It raises all sorts of policy problems as well as system complexity problems in terms of monitoring and managing access to the high priority queue. The paper there from Casey and Dave is a good, almost 10 years old history lesson on why that has not worked on the internet. Other attempts, the heavy hitter filter and Cisco's dynamic packet prioritization, both mechanisms to try to differentiate between what they refer to as elephant flows versus mice flows. And here, mice flows were, elephant flows were the bulk data traffic flows. Mice flows were intended to be the smaller flows that get stomped on by the elephants. Problem was it was the wrong metric. It instead of using something like low data rate, used a small transfer size. So a flow would get high priority for some small number of packets, maybe 100 packets, and then it would go into the low priority bucket. So something like a voice over IP session, the voice stream of a Zoom call, a multiplayer online game, you've got prioritization for the first few seconds, and then you're stuck with the elephants. The next, a couple of concepts, one called RD and one called loss latency trade-off, introduced a secondary shallow queue that went alongside the default best effort queue, but introduced some degradations to that shallow buffered queue. In the case of RD, it got low priority compared to the default queue. And in case of the loss latency trade-off, um, high packet loss was the downside to choosing low latency. But that Lola proposal was actually relatively close to the what we ended up with NQB, and the lead author of that actually became one of the co-authors for the NQB draft. Um, the concept was inspired really by FQ-Coddle's prioritization of sparse flows. And if you're not familiar with that, the idea there is that a flow that is this is kind of the simplified version of it, a flow that is effectively using less than its fair share of the bottleneck bandwidth gets high priority. And then all the flows that are capacity seeking and are effectively using their fair share get lower priority. And so can we achieve similar results to that, but without using FQ? FQ, as Dave was just talking about, um, works very well in certain contexts, not really optimized for high performance, low cost hardware, um, and also has some issues with VPN tunnels and things like that, but we want to have an alternative that could work well in low cost hardware and achieve great performance. So the definition of NQB is in a sense that you provide these two equal priority queues. They're both at best effort, so it's not a high priority queue and a low priority queue. It's just one with a deep buffer and one with a shallow buffer. The deep buffer queue is called the default queue, and the shallow buffer queue is the NQB queue. Um, and you can allow each application to choose which queue works best for it using a diff code point. Now, there's some additional requirements and recommendations in the draft. There's this concept of traffic protection, and that's a strongly recommended feature that an NQB network node supports. And that's some mechanism to automatically monitor the traffic that's entering the NQB queue. And if a queue starts to grow, mitigate that by redirecting the traffic that's causing queue growth into the default queue. Um, and the draft gives some examples of algorithms that can be used for that, in particular, one that was designed for DOCSIS networks. Um, and you notice there's an asterisk on the word choose, allow each application to choose, which brings us to the next slide. Um, there are some requirements for an application microflow to be eligible to be classified into the low latency queue or the NQB queue. It has to be both low rate and non-bursty. So the text in the draft reads that the rate needs to be less than about 1% of the typical network path capacity. And then it provides an example that works out to roughly 500 kilobits per second today. You notice that's sort of a fuzzy definition. It's intentionally written in terms that can evolve as network capacities evolve, but even so, it's fairly fuzzy, not a bright line, and that's intentional. Uh, the idea is that an application, when it's choosing what code point to put on its packets, that choice could be made at compile time. That choice could be made at runtime, or there could be configuration options for the user. But typically, there's going to be very little information that an application has in order to know exactly what network paths it's on and make that decision based on the actualities of the environment. So the idea is to encourage application developers to be conservative here um, and ensure that there are downsides if an application is sending data that's too quick, too fast, or too bursty. That would cause queue to build up in the network that it's on. The other reason why it's fuzzy is that this isn't a guaranteed service. This is an alternative to a deep buffer default service, which um, is almost guaranteed at certain times to have significant buffering delay, and this provides an alternative which the vast majority of the time is going to provide significantly better latency, jitter, and packet loss for flows that are both low rate and non-bursty. The non-bursty requirement is written in terms of a rate equation that the bytes sent in any time interval need to be less than or equal to the R times T plus 1 MTU, where R is the rate mentioned in the first bullet. So if those two statements are true, then a microflow can be marked as NQB, and the diffserv code point 45 has been assigned by IANA for this purpose. Okay, we're talking about diffserv code points. How does this relate to diffserv as we know it? So I think everyone's probably aware that diffserv has traditionally not been used on the public internet. It's frequently bleached or cleared to zero on ingress by at least half of networks. Um, uh, and there are varying views on if that's the right architecture for the internet to be bleaching diffserv code points, or if it's the wrong architecture. And there are all sorts of viewpoints on what diffserv should do and how it should be used. But in large part, um, it at the end of the day is used as internal marking in metro networks, enterprise networks, campus networks, things like that, and not peered across the internet very much. Um, Part of the reason for that is that the historical definitions of standardized per hop behaviors and code points revolved around wants and needs and less around characteristics of the actual traffic. So an application could use a diffserv code point to request certain specialized treatment by routers, expedited forwarding, assured forwarding, etc. These commonly equate at the end of the day to priority. And so using priority signaling and across multiple different management domains is really infeasible. First of all, it's non-verifiable. Packet enters a network. It's difficult to know whether that packet is allowed to get the priority that it's asking for. Um, and since it's playing in this zero-sum game space of prioritization, where if you're not getting priority, you're getting deprioritized. And so the incentive is to increase your priority in order to get good performance for your traffic. And so that requires the whole control and policing infrastructure and management around it. Um, where NQB sidesteps that problem is rather than it being an application's request for high priority from the network, it's the application making a statement as to its behavior, that it is low rate and non-bursty. And so this is a verifiable behavior that any network node could monitor for individual flows um, uh, and validate against those requirements. There's no incentive to lie, so this is not a high priority queue and a low priority queue. It's just a shallow buffered queue and a deep buffered queue. If your application is sending traffic that is bursty or high data rate, and you don't want to suffer excessive packet loss, then you're better off choosing the default queue. Default queue is a great queue for classic congestion control, a great queue for Cubic and Reno and BBR. Um, no advantage to those kinds of applications to mismarking their traffic. Um, and then there's this function called traffic protection, which is a backstop to prevent issues arising from inadvertent mismarking or malicious mismarking of traffic to protect the latency in that NQB queue. Um, in core networks or network links that are not bottlenecks or not expected to be bottlenecks, the NQB traffic is aggregated with the default queue building traffic in those core network links. All right, what's the relationship to L4S? So these two concepts kind of came about around the same time. Um, NQB, just to you put it on one slide, is intended only for low data rate applications. And L4S is intended for high data rate applications. That's sort of an oversimplification. Um, L4S provides the congestion feedback that a application needs in order to adjust its rate based on the available capacity, where NQB is sort of a set the code point and send, and you do your homework ahead of time to assure that that you're unlikely to be causing a queue. Um, but only intended again for those low data rate applications. Now, in the network, a dual queue implementation could implement support for both NQB and L4S, with both types sharing a low latency queue. That's in fact what we do in low latency DOCSIS. And potentially an application could mark its packet both with the NQB code point and marked as L4S using the ECT1 value in the ECN field, but only if it complies with both sets of prerequisite requirements. So it would have to be low data rate, non-bursty, and support all of the L4S requirements around rate adaptation. Um, and so one question that I've gotten a number of times is, well, why not just use ECT1 instead of a diff code point? If you're saying that both types of traffic could go into the low latency queue in a dual queue node, why not just have this low data rate traffic mark itself as L4S? A couple reasons for that. One is sort of the standards and architecture reason that the prog L4S requirements in RFC 9331 aren't written for low rate flows. The requirements are around must provide congestion feedback, must be replaceable with a classic congestion controller, must detect non-L4S ECN in the network, must converge to RTT independent rate, etc. These requirements are not appropriate for these very low data rate flows. But that's not a super strong reason. Certainly we could write the prog requirements in a way that that supported very low rate flows, like comply with the NQB requirements. But there's some pragmatic reasons as well. First one is Wi-Fi. There are hundreds of millions of Wi-Fi networks around the world that today don't support L4S, but they do support multiple queues and use diff-serve code points to select to map packets into those queues. And the code point that's selected for NQB maps into a separate queue from best effort traffic. Also, the implementation and adoption complexity. Some of the applications that are great candidates for using NQB don't implement a traditional congestion control mechanism. They're either very low rate, kind of a ping pong application that has one packet in flight, or a very small number of packets in flight. Think of things like DNS lookups, or they're fixed low rate applications or slightly variable low rate applications like multiplayer online games or voice over IP, these kinds of things where there's not a lot that the application can do in order to adjust its rate in a kind of traditional classic congestion control sense. All right, so, last slide. The IETF process and current status. So this draft has gone through a very lengthy review process in the IETF Transport Working Group for many opinions expressed and many revisions to the draft. In fact, this is only the second diff-serve code point that has been defined by the IETF in the last 20 years. So there's not kind of a tremendous push in the IHF to come up with new and interesting ways to use different code points. And there's a lot of skepticism, I think, around DSCP in general. But hopefully, with the definition in NQB, that it enables end-to-end usage across the internet because it sidesteps a lot of the issues that the previous code points have had. Current status is we finished the working group stage, and it's kind of the turning the crank at this point through the final IESG and IETF approvals. Everything goes smoothly. Expect to have an RFC early next year. The code point 45 is now listed by IANA as being assigned to NQB. And we also have started to get announcements of network operators that are peering DSCP 45 across their interconnects with their peering partners as early this year. So that's it. There's time for Q&A. I don't know if there is, but
Thank you
turn
very
it over.
much, Greg. We are 1 minute over time, actually, so I think maybe we'll do the Q&A in the chat or in the Q&A tool if you have time for that there. Thank you very much.
Absolutely. Thank you.
Our next speaker is Stuart Cheshire. He is Apple's distinguished engineer for networking, and we'll be talking about intelligent buffer source management to minimize total network latency. So, Stuart, please take the stage.
Thank you, Bjorn. Hopefully you're hearing me.
I can hear you well.
All right, let me share my screen. All right.
Those slides.
Excellent. Good morning, good afternoon, good evening, everybody, wherever you're in the world. My name is Stuart Cheshire, and I'm a distinguished engineer at Apple. So this presentation starts with a story. It goes back to 2011. I was working with screen sharing on macOS, and it was really sluggish on slow networks. Now, you might think on a slow network, you expect things to be sluggish. That's what being slow means. But when I pinged my Mac at home over its slow DSL line, the round trip time was about 50 milliseconds. But when I clicked on the menu with my mouse, it took 2 seconds for the menu to appear. And I just learned about buffer bloat from Jim Geddes, and I thought this is classic buffer bloat in the network. But when I measured the round trip time, it didn't match. And I investigated a bit more deeply, and it turned out, in this case, the problem wasn't in the network. The problem was on the sending machine. So in this case, going back 10 years, it had the default socket SO send buff size of 128K. And the socket send buffer is important because you want to buffer data that's in flight to keep the bandwidth delay product of the pipe full so that you're fully utilizing the available capacity. But in this case, over a 500 kilobit DSL line with 50 millisecond round trip, that's about 3 kilobytes. That's about 2 packets for enough to keep the pipe full. So the other 125K of the socket send buffer was just stale data. And what would happen is the screen sharing client would grab a frame, compress it, write it to the send buffer. And K event or select would say, yeah, this socket's still writable. We've got more memory. So the screen sharing would grab another frame, compress it, write it, and it would go around this loop, filling up the whole send buffer with frames waiting to go out. But these frames hadn't even left the machine yet. And every frame that screen sharing compressed and enqueued sat in the send buffer for 2 full seconds before it even left the Ethernet port. So when you add a 2 second lag on every frame, it's not surprising that usability is terrible. So just a month later, working with some of the other networking engineers at Apple, we came up with this idea of this socket option called TCP not sent low watermark. And with that option, if it's enabled by the application, K-Event won't report your socket as writable just because it has RAM available. It will wait until the unsent backlog has almost run out and TCP is about to need more data to send. And then the socket becomes writable and the screen sharing code grabs a frame, compresses it, and writes it to the buffer just in time when it's ready to go out. And with this socket option, the picture looks more like this. You still have whatever it takes to keep the bandwidth delay product full, and then a little bit more waiting to go out, not hundreds of K. So I'm describing work from a decade ago. Some of you have probably even heard about me talk about this before. So why am I talking about this now? Well, one thing we realized fairly soon after working with this is that we wished we'd specified the low watermark in terms of milliseconds rather than bytes. And 16 kilobytes empirically worked great for screen sharing, but on really low networks, low rate networks like Thread, a 0.25 megabit or less, 16 kilobytes is still a lot of delay. And on multi-gigabit links, 16 kilobytes is almost nothing. And an application would like more notice because once K-Event reports an application as writable, the scheduler's got to schedule that application. It's got to actually do the work it needs to do. In the case of screen sharing, grabbing a frame and compressing it, that does take a little bit of time. It's doing video compression. So what we really want is a fixed time budget where the application says, give me 20 milliseconds notice of when you're going to need data. So that's one thing we kind of wish we'd done differently. The second thing is more important. Just this year, I was working with Bob McMahon, who's the maintainer of iPerf 2, and Bob was adding some working latency measurements to that. And of course, if you want to measure the latency, you want to minimize any self-induced latency at the source. So I told him, we have this thing, TCP not sent low watermark, and it's implemented on Linux too, which is great. And he tried it, and the behavior was very different. And this led to some discussion. And after a few mails back and forth, we discovered that when I heard that TCP also had TCP not, when I heard that Linux also implemented TCP not sent low watermark, I'd been really happy initially, and I hadn't investigated closely enough. And it turns out that while the similarities, there are important differences. On Mac OS, the socket option determines a low watermark. And when the unsent backlog falls below that low watermark, the application is signaled so it can choose how much makes sense to write for the next chunk. On Linux, the socket actually determines the high watermark of the maximum the application is allowed to write. And if you set that to 16 kilobytes, there is a little bit of a rounding. I think it's rounded up to a whole number of mbuf chains. But if you set the socket option to 16 kilobytes, you prevent the application from doing large writes, and it has to spin, doing lots of little small writes, and that really hurts the throughput. So that's unfortunate, and I'm grateful to Bob McMahon for being the catalyst that uncovered that. So this gives us an opportunity to revisit this and do something better. We have three goals. One is obviously, let's all agree on what is the right behavior across all different platforms and do it the same this time. Let's take this opportunity to make a new API that specifies a notification time that is required in units of microseconds or milliseconds, not in terms of bytes. And The other important difference is when we did this 10 years ago, Quick did not exist yet. But Quick is increasingly popular and it's a very good protocol. So if Quick doesn't have a similar mechanism to avoid inadvertent buildup of a backlog at the source, Quick is going to have the same problems for real-time applications that TCP did 15 years ago. And there's some very interesting work going on for media over Quick that really needs low latency. So uh, not just TCP, we would like all transport protocols on all operating systems to provide better feedback to the applications so they can avoid inadvertently building up a big backlog. So to this end, we are starting some new IETF work. Just yesterday, I submitted an initial version of an internet draft for source buffer management. I have requested a new IETF mailing list for interested people to discuss this. This is not live yet, but if you look again next week, that mailing list should be active. And our plan is to work together on a document to present at the next IETF meeting in Bangkok. So call to action. Keep an eye out for the creation of that IETF mailing list. Please read my draft and send feedback on it. If you're going to be at the IETF in Bangkok, please come to the transport area meeting. If you're a networking implementer, please implement this new option, whatever we decide it is at the end. And if you're writing network applications that are delay sensitive, make use of this option and spread this word to your friends who are also working on delay sensitive applications. Thank you for listening. Bjorn, do we want to, if there are no questions, we can move on to the next one, I think.
Sorry, I lost you there. Can you hear me now?
I'm hearing you now.
Very
I
good.
hope, I hope my audio is coming through, I hope.
Yeah, yes, it is.
Oh,
I just
good. Oh, good. Okay.
Zoom dropped the call from me, but it put me back in very quickly. There's a question in the chat. Do you have a view on how the time-based target would work for links with variable link speed, like mobile networks and Wi-Fi?
Good question. And this is why we're having some IETF work, because I'm I'm not assuming I can work all of this out myself. I want to create a team effort where people contribute thoughts. I can give you my initial thoughts on variable speed links. Remember, this this property we're talking about is buffering at the source. Many of the things we talk about in these understanding latency workshops are about L4S and LibreQoS and Cake and all things that affect properties in the network. And this is great, and I've worked on that. What we realized with this screen sharing problem is that we're at a point in history now where there is really good momentum with fixing buffering in the network. And that's going to improve network round trip times. The trap we risk falling into is we'll run benchmarks. We'll look at TCP level round trip delays and we'll celebrate and say, we fixed the problem. We don't have buffer bloat in the network yet. And people run applications and they'll still suck and they'll be very disappointed. And that problem is excessive buffering at the sender. And it's sort of ironic that we fixed the whole network, which is really a big job. And if we neglect fixing the buffering on the sender, then it's all for nothing. So getting back to this question, what about variable speed links? Well, variable speed links are a challenge, but they're already a challenge for the congestion control algorithms, we're using TCP and QUIC. And people know I hate the term congestion control. I think it's very misleading. I prefer to call it rate adaptation because that's what it is. It's the algorithm that decides what rate to send the data. And those applications have to track changing rates for Wi-Fi or cellular, especially radio technologies, but even other links can change rates when your share of the rate changes, when other flows come and go. So whatever that rate adaptation congestion control algorithm is doing to determine the rate at which your device sends out packets, it should continue doing that. What we want is the software API to give some feedback to the application that says, if you care about delay, you should stop writing data right now because none of it's leaving the machine. It's just piling up in a queue because the congestion control algorithm says we can't send this now because we will overflow the network and cause packet loss if we do. So the congestion control is gracefully metering out the packets. We need that back pressure to bubble up one layer to the application and saying, hold your horses, we're not ready for the data yet. We'll let you know when you're ready. And then you can generate fresh data just in time instead of stale data that sits in a queue. Hopefully that makes sense.
That makes perfect sense. Thank you very much.
Thank you.
And I see Neil joined us just in time. Our next speaker is Neil Cardwell, who's a principal software engineer at Google, and he will be presenting how BBR congestion control tackles latency. So Neil, if you are ready, please take the stage.
Great. Yeah. Can you guys hear me?
I can hear you, yes. We cannot
Okay,
see you
great.
though, but up to you.
Okay. Yeah. I think I'll just skip the videos and
Fine.
just project the slides if that's cool. All right. Let me. Are you guys able to see the slide there?
Yep, it's
Okay,
working.
great. Great. All right. So thank you very much. My name is Neil Cardwell, and on behalf of the Google BBR team, I'm going to talk today about how BBR congestion control tackles latency. And this, of course, is joint work with the BBR team at Google, listed here. Yeah, let me just dive right in. So let's talk about the problems that BBR is tackling. So the problems that motivated BBR go back to around 2013, when we were seeing many Google services complaining about TCP and quick performance. And on our internal backbone called B4, which is built out of commodity switches, we were noticing that TCP throughput was often less than around 10 megabits when the links were much faster than that, many orders of magnitude faster than that. We noticed on YouTube, sometimes there was terrible video quality and sometimes round trip times, ping times, if you will, of greater than 10 seconds, sometimes up to 30 seconds. And we were also seeing sometimes that Google.com as a search experience was having poor latency in developing regions. And we started to see services start to work around TCP by using parallel connections or tweaking various TCP knobs, or we would see ISPs add more buffer to the network. All of those were due to a root cause of basically the fact that TCP congestion control at Google and in the world, in the Linux default, for example, was cubic at the time. And cubic is what we could call a loss-based congestion control algorithm, where packet loss is the sole signal of when to slow down. And the problem with that, the problem with loss-based congestion control in general, is that it keeps sending faster and faster and faster until it sees a packet loss. And that's widely deployed. That's a widely deployed approach. It goes back to Reno, the very first congestion control for TCP in the late 1980s, and has continued through the current internet default, which is cubic, used on all the major OS implementations out there. But it turns out that packet loss alone is not a great proxy for congestion. And there are problems at sort of two ends of the spectrum. In what we could call a shallow buffered situation, where the bottleneck link has a very shallow or small buffer for packets, um, connections can frequently suffer what is essentially kind of random packet loss. And as a result, because they're loss-based, they can suffer low throughput. And we can think about this as basically because that in such scenarios, packet loss happens before the link has reached sustained full utilization. And if we take a concrete example, we can take a case where perhaps an internet path has a 10 gigabit bottleneck link and it has a 100 millisecond round trip time, then Cubic would need a very, very small packet loss rate of, 0.30, like 5 zeros and then a 3. I think it was 1 in 3 million, 1 in 30 million, something like that. And of course, really, in the real world, it's infeasible to reach a packet loss rate that's that low. Um, and instead, in the real world, for the public internet, where the packet loss rate is typically around 1%, Cubic will typically get around 3 megabits. So that's one end of the spectrum. And the other end of the spectrum, in deep buffers, flows suffer packet loss while maintaining high queuing delay. And that's because essentially in deep buffers, packet loss happens well after congestion, and loss-based congestion control keeps ramping up, building higher and higher queues, suffering higher and higher delays. And this is a problem that people have dubbed buffer bloat and has been discussed in the community since around 2011 or thereabouts. So what's going on here? With congestion control, it's often helpful to have a very simple mental model like the following. So we can imagine basically a sender over here on the left that's sending these gray packets through the network, and somewhere in the network there's a bottleneck link, a slowest link. And if the sender that you can sort of see here with the arrow, and if the sender is sending faster than that bottleneck link can deliver packets, then a queue of packets will start to build up here in front of that bottleneck link. And then the packets will make their way through the network. They'll be received by the receiver. The receiver will usually send acknowledgments saying, hey, I got this packet. And those will make their way back through the network on the return path. The sender will see those ACKs and it will use those to decide what was delivered, what was lost, and how fast it should send. And so if we think about the dynamics of a simple model like that, we can sort of look at what happens as a flow starts up and sends using two different graphs or diagrams. So both of them have on the x-axis the amount of data in flight in the network. And then there are two graphs. The bottom one here is the delivery rate, the achieved bandwidth of a connection. And the graph on the top is the round trip time, which you can think of as sort of the ping time for packets traveling over that path. And if we imagine a connection starting up and with some small amount of data in the network, the initial congestion window, say, and it's ramping up, sending more and more data, eventually it will hit a point where it is sending at the fastest rate that the bottleneck link can deliver packets. And at that point, its delivery rate has reached the maximum value. But as you put more and more packets in the network, those just sit at that bottleneck queue that we were looking at in the previous diagram. And those extra packets cause higher and higher queuing delays, which add more and more delay to the round trip time, until, if we're using Cubic or Reno, something like that, a loss-based congestion control, eventually the queue of packets will reach the bottleneck buffer size, and you'll start to encounter packet loss and maximum delay. So what happens in these two scenarios that we've been talking about? So in a shallow buffered scenario, what happens is that the multiplicative decrease upon these random burst losses leads to poor utilization. And so with Cubic or Reno, actually you're going to spend a lot of your time down here with a low amount of data in flight and a low throughput because of these multiplicative decreases upon the random loss. Now, what is the optimal operating point? The optimal operating point is, you've probably figured out intuitively that it's this point here at the sort of knee of both curves where you've achieved the maximum bandwidth and you still have the minimum round trip time. And there's some nice work done by Kleinrock at UCLA and his grad students in the 70s and 80s, sort of proving this out mathematically. So how can we achieve that operating point? So the basic approach that BBR takes is that we try to estimate this point, which has been known by the community as the bandwidth delay product, the what you get from multiplying the round trip time times the available bandwidth. We try to BBR tries to calculate that as the maximum bandwidth recently achieved times the minimum round trip time recently observed. And how can we get that? Well, the approach that BBR takes is that we look at the windowed minimum of recent RTT samples and use that here, the red RTT sample, as our estimate of the minimum bandwidth. And then we look at the windowed maximum of bandwidth samples that we've recently seen and use the maximum bandwidth that we've seen, the red dot here, and use that as our estimate of the maximum bandwidth. And it turns out it's a little bit interesting here that when you're on the left side of the BDP here, only the minimum round trip time is visible. You've got a small amount of data in flight, so you can't actually see the achievable bandwidth. And when you're on the right side of the BDP, only the maximum bandwidth is available. You can't really see the minimum round trip time because there's some amount of queuing. And so a flow has to spend some of its time on the left of the BDP and some on the right of the BDP to sort of understand the network path. And that is exactly what BBR does. It basically dynamically models the network path, controls its sending rate based on that model, paces near its estimate of the maximum bandwidth available to the flow, and bounds the amount of in-flight data with the congestion window as a function of the estimated BDP. And it tries to sequentially probe, going back and forth on the left and right of that diagram, to probe both the maximum bandwidth and minimum round trip time and feed those into the model. And it tries to seek a high throughput with a bounded small or reasonable queue. And in practice, it tends to approach the maximum available throughput for some targeted level of random loss, and it tends to be able to bound a queue to a reasonable level independent of the buffer depth. And so what does that look like if we think about it as a system? It's basically some input signals that the connection is finding in the network in terms of throughput, round trip time, loss, ECN, things like that. They feed into the model of the network path, and then that model is passed to a probing state machine that explores the network by increasing and decreasing the sending rate using a pacing engine that's taking the input data and then pacing it out into the network. And what does that look like if we run some experiments to sort of highlight the properties of the algorithm? So we can show in some sort of simple experiments that BBR can bound the queuing delay to a reasonable level despite any amount of bloated buffers. If we run an experiment like this, where we run 8 bulk flows with buffers of various depths, and then we look at the RTT latency here for the different scenarios, and we compare BBR in green and cubic in red, and we can see that as we expand the buffer, cubic fills that buffer and creates larger latencies, whereas BBR keeps the latency at a constant value that is a function of the BDP. And if we think about the sort of shallow buffer scenarios where you might encounter random packet loss, we can run an experiment where we vary the loss in a controlled fashion in a lab environment. And we can see that, indeed cubic, as the loss rate gets to be even 1/100% or 1/10%, it's achieving a very low throughput, whereas BBR can achieve a very high fraction of the available bandwidth up until some configured amount. And so in a nutshell, the recent versions of BBR are aiming for high throughput, bounded queuing delay, and then the thing that we've recently added in recent versions of BBR is to aim for a usable coexistence when sharing with the legacy Reno and cubic congestion control algorithms. And as mentioned before, this is a model-based approach, and the things that we've recently added to the model are estimates of the maximum amount of in-flight data that we can maintain before the loss rate or ECN mark rate becomes too high, and other elements of the model as well. And over time, we've continued to iterate on the algorithm and the code. We've open sourced versions of BBR for TCP, Linux TCP, and for Quick. And we've iterated through BBR version 2 and version 3. Currently, we're at BBR version 3, and it's a working group item at the IETF. We hope to publish an experimental RFC kind of documenting the algorithm. You're welcome to check it out on GitHub. You can see the current version of the text and offer comments or suggestions or edits. And the editors are listed there. It's a cross-organization effort. And then, if we'd want to do a quick comparison of congestion control algorithms for the public internet, just as a quick summary, we can view the behavior of Reno congestion control, which was the original one, as we mentioned, and is still the theoretical IETF standard. We can view its behavior over time with time elapsed on the x-axis, and on the y-axis, we can have the volume of data in flight in the network. And as the Reno flow starts up, it sort of grows exponentially until it hits packet loss and enters a fast recovery to recover those losses, at which point it cuts its sending rate in half. And then it sort of slowly, linearly ramps its congestion window back up until it hits packet loss. And then it repeats in this sort of sawtooth pattern. And this is the behavior that gives it high latency and deep buffers as it climbs up this sawtooth without regard to the queuing delay. And then because it's a growth of 1 packet per round trip time, it's a very sort of non-scalable linear growth that needs 10,000 times more time to reach 10,000 times higher bandwidths. And it has that sort of low loss tolerance that we discussed because of the large multiplicative decrease in any round trip or packet loss. And Cubic is sort of similar, except it has a more intelligent growth curve of the congestion window as it's probing for bandwidth. It sort of rapidly returns to the last known good value and gently expands beyond that, accelerating until it hits loss again. And that definitely gives you better utilization of the bandwidth, but it's still not great in terms of its scalability and still has low loss tolerance. So BBR, by contrast, has a similar startup behavior, but then after that, it sort of gently increases the amount of data in flight and pulls it back down using pacing. And then if more bandwidth becomes available, it grows exponentially here. And that can allow it to have a sort of bounded latency even in deep buffers, and scalable exponential growth if more bandwidth is available, and allows it to be more loss tolerant up to some configured level. So in conclusion, BBR is a model-based congestion control, and we deployed it at Google, and other folks have deployed it as well. It's open source for folks to use, and it's under work at the IETF Congestion Control Working Group, you can follow these links for more information. And what we're working on now is versions of BBR that could work with recent IETF standards called L4S for low latency, low loss, and scalable throughput. And we're always working on reducing packet loss and latency and improving coexistence with Reno and Cubic. And as always, we welcome feedback and open source contributions from both the research and user community. So thank you very much. If there's time, I'm happy to take questions.
Thank you very much, Neil. It's very, very interesting stuff. There are a few questions. We're slightly over time, but we'll take some of the break to answer the questions. So there is a question here from Bob McMahon. Are there effects on BBR model when the round trip is asymmetric? So when the one-way delay is not one half of the round trip?
To our knowledge, we haven't seen effects from that. The you know the dynamics usually can be fully analyzed in terms of just using the round trip time. But if people have seen effects in their experiments, we'd love to hear about it.
All right. And then there's another question from Sebastian Muller here. What windowing is used for the RTT estimate? Is it an exponentially weighted moving average or something else?
So for the RTT, the minimum round trip time estimate is a windowed estimate over the last 10 seconds of measurements. That's because we really would like to get the two-way propagation time through the network, and we really would not like it to include any of the queuing delay. And if, for example, if you use an EWMA, which is used for TCP's smooth round trip time, then that would tend to pick up a lot of the queuing delay that a flow would tend to see. So that's why we use the minimum over the last 10 seconds.
All right. And then Saidi Raj is asking, what scale of networks really benefit from BBR versus cubic versus Reno? Any minimum number of nodes or even a single node with some traffic types?
Um, I think, any scale of network could benefit. The two kinds of scenarios where we've seen the biggest benefits and where we, would expect the biggest benefits are one in shallow buffered scenarios. So let's say you take a commodity switch and you use it to build a high-speed network at, say, for a research lab for scientific research, or for a big cloud provider. If you have a large wide area network built out of shallow buffered switches, then you'll see the benefits due to BBR's improved handling of random packet loss. And then the second scenario where we see big improvements is in the last mile of the public internet, which often has over provisioned buffers that cause the buffer bloat phenomenon that we and others have been talking about at this webinar. And so BBR, in a sort of typical over buffered last mile link, is able to bound the amount of queuing at a more reasonable level, keep queuing delays lower, which is more beneficial for cross traffic that might be latency sensitive, either people browsing the web or using Zoom, things like that.
I see. And then Randall is asking about how BBR works with real-time things like WebRTC.
Yeah, that's a great question. So the current BBR algorithm is not designed with things like WebRTC in mind, and so it has some aspects that don't really work well with real-time traffic due to the way it cuts the congestion window periodically to try to rediscover the minimum round trip time. That's sort of the way that's tuned is more for web traffic and video streaming traffic, video on demand traffic. It's not really tuned for real time traffic. I think that's tuning some variants of BBR to work well with real time traffic is sort of an open area of research that people have looked at, but we don't have a good final version that works well with real time traffic.
It's a very good point. And also, final question, I think, is when do we expect BBR3 to land in the Linux kernel?
Yeah, as soon as we can, make it happen. It's unfortunately, there's a lot going on in our team and few resources for the um, legwork on the ground to make that happen. So I can't unfortunately give you an ETA for that.
All right. Thank you very much. That leads us to the break. I think we'll try to stick with the schedule and start again in about 5 minutes at 17:20. I'll put up the agenda while we're on break so that people know what's coming up. Okay, we're coming up on the end of the break here very soon. You're ready, Christian?
Hey, Björn, can you hear me?
I can hear you loud and clear.
Very good. Let me just try to, maybe I should turn on my camera as well.
I can see you now.
You can see me? Very good.
Yes, I can see you.
Okay, very good. Let me just also start the sharing, right? Let's see.
So I'll introduce you first. Our next speaker is
go
Christian
ahead.
Anderson. He's a strategic product manager in the Ericsson Product Area Network organization, and he'll be talking about 5G and latency explained. Now the stage is yours, Christian. I'll
Thank
stop
you.
sharing so you can show your slides.
So let me know when you see it.
Yes, that's showing.
It's good.
Yep, working well.
Okay, thanks for having me on the agenda. And very interesting to hear, of course, all the previous speakers here and about what they're up to. So what I would like to talk about here is a little bit about, like a high level view or like a helicopter view, you can say, of how we are working on latency from a 5G point of view, and of course, especially within Ericsson. And this is one area that we are kind of investing in. So I would try to explain a little bit our systematic way, how we are dividing or separating the problem, right? And also, what we are doing actually. So I will show you actually what the features we have that we already have in our products actually that are available. So they are part of our product, these features, but maybe, then of course the carriers need to deploy them as well in their network. So that is might not have happened yet in certain networks, right? But we have them as part of our products, and they are available for operators to enable them. But I think just give you some background, right? So I hope you can see the slides here. So we call this area for time critical communication, and that includes also the 3GPP specific. I think you already all heard about the ultra reliable low latency communication standard that was set forth in the 3GPP to. And I think the important aspects of there is to deliver data within a specific time window required by a certain application. As it listed here in the slide, we have one example. Data can be delivered within 30 milliseconds within a certain reliability. Here it's down the below left here is listed like 99.9% reliability, meaning that 99% of those packets should be delivered within 30 milliseconds. So the presentation I have here is about what Ericsson is doing in the area of time critical communication and delivering data within a specific time window required by certain applications. But we are coming from this mobile broadband, and that is of course the bread and butter of our business, right? And I think if you take that into account, it's about maximizing data rates. Without any guarantee regarding latency, and that is kind of what we mean. What we mean by the best effort here. So our customers, they often try to squeeze in as much spectral efficiency as possible to be able to share that with their customers in the end. And so anyway, but this means that when addressing time critical use cases, there will be like fundamental trade-offs that needs to be considered between latency and other KPIs, such as the throughput, coverage, energy efficiency, and so forth. So with the time critical communication, the latency aspects will be prioritized over these other parameters. And that is the fundamental difference when comparing with mobile broadband, which is only focusing on delivering the peak throughput without any considerations of any bounded latency at all. So that is a little bit what we are trying to focus on, and you can see the illustration here. I mean, you have this long tail that you have, and you have this long delay variation and jitter, and then of course this is what we want to set some. I mean, be able to differentiate different services meeting certain delay variations. And having this bounded latency type, upper bounded latency bound that we want to, provide as differentiated services. So question is then, I think maybe in this forum everyone knows, but why do we want to do this then? So that is of course the next question that I want to address. So of course one thing is to enable new services. And then one thing to differentiate is, of course, on the latency. And we see also that a majority of some of the 5G applications that we are considering are time critical in its nature. They are demanding some reliable low latency. It can be very different between those different categories that I listed here. But I will go into a little bit more detail. So we have these 4 categories on a high level. We have the industry control type of use cases. We have real-time media type of use case where we have a cloud gaming, cloud AR, media production type of use cases. We have remote control of machines, vehicles, medical equipment, whatever, right? Where you have a person sitting somewhere, remote driving something that is a completely different area. And then you need to have a fast turnaround loop to be able to control that device. Another area is, of course, the mobility automation, and that is then, automated container transport in ports, AGVs on a factory floor, for example. Each category and use case here includes then, of course, a wide range of use cases, and with a range of time-critical requirements ranging from like tens of millisecond consistent latency down to, single-digit millisecond consistent latency then. So that is kind of, the reason. We believe that there is a value on enabling these kind of use cases to our customers then. So now I will try to explain it a bit. What is the problem with 5G and cellular then? Because now is a little bit of an animation here, but what we have done is that we have actually divided the cellular part into, a few key different areas to consider. And then actually, to address these different sources of delay in a cellular network, we need to actually have different features addressing different areas here. So you can see here in the picture, this is listing, RAN is, by the way, the radio access network, right? So that is only the radio part of the latency. So here we have divided that into 5 different areas, high-level areas here. So we have data indication delay. So that is mainly an uplink type of delay that comes from the UE. So the UE needs to tell the network when it has data to transmit. And that negotiation can take quite a long time, as you will see in an example that I have. The second part here is the queue delay. So that is when the network knows that there is data in the buffers, then it's like time to schedule that data. So that can, of course, be other users can be before that, and that will also cause, different times of delay. And also, of course, if we are pushing too much data, then with the available bandwidth we have, that will also cause delay. And here, we already talked in the previous presenters. He has been talking about the L4S, how to manage the queues, right, in the network, and that's actually one of the features that we are supporting in our radio access network at the moment. Another part is, of course, the transmission delay, and here it's more like you have the different frequency bands have a little bit different properties when transmitting. But that is actually, when you look at the overall view, that is kind of the small part here. But of course, if you look at the frequencies, low band, you have mid band frequencies, high band frequencies. Of course, there are different properties that are better. For example, for high band features, you have like lower latency, a little bit higher data rate. But in that sense, you get a problem with the coverage instead, where you have for the low band, you get a wider coverage and also a little bit more robust transmission in rural areas. That will also help the latency aspects. And then, of course, the mid band in the middle, that is also, I mean, excellent for urban coverage and also have a good capacity, good latency properties, and also a good range. The retransmission delay, that comes when you're, I mean, sometimes you cannot guarantee if you're in a bad channel condition, right, or not. And then you need to retransmit a few times before you actually will, the transmission has, been received correctly. And that will also have a certain delay here. And then the last part here I want to talk about is, of course, the handovers. I mean, if we want to build a large network, right, and we want to move freely between cells, but actually in the solutions we have today, when moving between cells, I mean, you're actually stopping the data, and then you're configuring the new cell, and then you're connecting to that cell. So that is having also an impact on the delay as such. So here, if we just continue a little bit, so this is kind of what it looks like today in a mobile broadband example. So you have to wait on your uplink resources from the network, and then you need to send the buffer data to the network, and then the network here can decide to schedule. But of course, if there are other users being scheduled in between, then you need to wait for that time. And then we can suddenly get like a handover interruption, and that can be in the range of 50 to 90 milliseconds. And then, of course, you can have multi-read transmissions between your channel quality, and that will, depending on the number of retransmission, that can take like 5 to 25 milliseconds, roughly speaking, depending on the channel quality you're in. So here I'm putting up kind of a range that we see today. Of course, I mean, you will not get the worst case that's very unlikely, of course, that getting the worst case in all of them. And in most cases, you're not, I mean, for example, this is covering the first one here, that is impacted by the number of devices you have. The second is, of course, devices and the number of and much data you have in the network. Handovers is related to the mobility. How often are you moving around between cells? And then, of course, the multiple retransmission is also related to the channel quality. So what we want to do is more this. We want to manage this delay from each of these contributors and get a kind of consistent performance with also for cellular users, so to say. So here I'm listing a little bit on what we're doing to address each of these type of sorts of delay. So here we have, for uplink delay indication, we have quite a few tools to address that. I mean, I will not go through them in details, but they can be used on a different level depending on the requirements you have. But it's like service adaptive type of features here that you can configure as you like to address these first, to avoid that you will get these long delays here up to 90 milliseconds, for example. So it will be more deterministic. If we continue, I mean, then the queue delay, I mean, of course, we have, I already mentioned that we are supporting now L4S in the radio access network here as well. On top of that, I mean, we have a lot of different schedulers that, I mean, we can schedule based on latency with like an earliest deadline first approach. We have a certain rate control scheduler. We can rate control, I mean, the scheduling to reach a certain rate. And then we have the priority here as well, where you can have a relative or absolute priority. And then, of course, the transmission, I think I talked a little bit here. I mean, this is kind of the small part here. I mean, it's just a few milliseconds here, but the frequency band, numerology, transmission time length, of course, the FTD versus TDD pattern matters as well. I mean, so we have these two methods here. I mean, frequency division duplexing and time division duplexing. I mean, those are the two methods used in wireless communication, and they differ then in how they allocate in the resources for sending and receiving data, where you have separate band for FTD for uplink and downlink, and TDD is a signal band. And then, of course, there's latency properties there as well. I mean, so that I mean, for more balanced type of traffic patterns. I mean, FTD could be more, since it's more symmetric, and then of course TDD is more asymmetric, so that makes sense for more asymmetric patterns. But then retransmission delay, I mean, we have features addressing that as well. Different link adaptation, robust encoding, modulation schemes is something that we are having as well. And then last but not least, we're also introducing a new handover here. Since I said that, I mean, the handovers can lead to large signaling overhead and a long connection interruption time, and sometimes as high as up to 90 milliseconds. So we're having a new way of doing handovers here with shorter connection interruption as well. So this shows a little bit of the problem in cellular aspects and what is causing jitter and delay of different aspects, and how we kind of are addressing these problems with different features there. So if we just continue here a little bit, I mean, we have also a little bit of a result. So this is one like a gaming application. We are generating some congestion in the background. So here is the L4S feature that we're using. So you can see here, I mean, the orange part here is the run trip time latency that we have. You can also see the CE marking is the red dots. And you can see that, I mean, there is a few spikes, of course, in a few places here. But if you compare to the baseline configuration, I mean, I think we are quite happy with the result as we see it as of now here. And you can also see that also the bitrate is being adjusted according to the marking here. So just showing one example of how the performance looks like here with one of the features. So I mean, just to summarize a little bit, then I mean, so we want to enable service differentiated cellular network, and we want it also to be very configurable, right, and being designed for certain performance levels. So we want, I mean, enable applications then to dynamically request the mobile network for connectivity type that fits these required performance levels for a certain application, right? We see that many emerging existing use cases requires deterministic latency performance. And some existing use cases, then I mean that we can improve the quality of experience of those existing use cases with having a more deterministic latency performance. And as I showed you in the previous slide, many features are already implemented and addressing different parts of the delay from the cellular network as we see it today. One thing, at least from our point of view, I mean, those features that I talked about are primarily developed also for 5G standalone deployment. So that is kind of the main configuration, and that is opposite then to like non-standalone deployments that we have as well, where you are relying with 5G on top of like an LTE anchor leg. You have the control channel on the LTE, but you have a 5G user plane set up as a separate leg then on the 5G NSA network, so to say. So this is kind of what I wanted to share here in this meeting today. I don't know if there are any questions or comments.
Thank you very much, Christian. Very interesting stuff. There are a few questions in the chat, but we are a couple minutes over time as well. So if you can please address the questions in the chat, and we'll move to the next speaker. Thanks.
Okay, sorry for that.
No problem. Our next and a final speaker for today is Simon Sundberg, who's a PhD student at the Karlstad University. And he'll be talking about measuring network latency from a wireless ISP, variations within and across subnets, with data from LibreQS, I believe. So Simon, please take the stage.
Yes, thank you, Björn, for the introduction. And not actually with data from LibreQS, but working together with some people from LibreQS. And
I see.
I'll get into it a bit later. But yeah, so I'm gonna share some work I've been doing together with my colleagues on measuring or monitoring the network latency from within a wireless ISP network. So I think most of the people that are attending here are sort of already aware that network latency is important and that it matters. So I'm going to jump straight into sort of how to actually monitor network latency. And there are many tools that you can currently use to actively measure network latency, for example, ping or IRTT. And these tools are great for testing network latency, but I would argue that this is not really monitoring network latency, because these tools won't tell you the latency that actual application traffic experiences. It will only tell you what these latency probes experience. And as Benoit explained yesterday, there are several reasons that these measurement probes may experience different latency than the actual application traffic. And one of the big factors there can, for example, be due to load balancing. So what you can do instead of active measurements is that you can use passive measurements, where you simply observe the latency that already existing application traffic actually experiences. And these passive latency measurement approaches have typically had fairly high overhead, but in the last few years, we've seen some new solutions that utilize technologies such as P4 and eBPF to drastically reduce the overhead of doing this and enable these passive solutions to scale to much higher packet rates. So one of these tools or solutions is the Evolved Passive Ping or EP-ping tool that we've developed. EP-ping passively monitors TCP round-trip times by essentially measuring the time between when we see a specific TCP segment and when we see the corresponding acknowledgement to that TCP segment. And as we do this entirely passively, we only observe packets. This is entirely transparent to the network. We don't need to collaborate with the end hosts in any way. And as long as we can see traffic going in both directions on the network, we can also get the latency measured on sort of either side of our observation points. Now, the sort of fundamental idea behind EP-ping is not particularly new. It's very heavily inspired by some previous work by Kathleen Nichols and her passive ping or p-ping tool. But the big difference really is that we implemented this tool in a technology called eBPF, which basically lets it run as part of the Linux kernel network stack. And by running this inside the kernel, we can drastically reduce the overhead, as we no longer have to rely on packet capturing and clone a bunch of packets. But we still keep it compatible with the Linux network stack. So it's not like some of these kernel bypass technologies where they take complete control over the interface. Now, another thing we've done specifically with EP-ping is also that we've added the capability now for it to aggregate these measurements on a per subnet basis directly inside the kernel. And this also helps reduce the overhead, as we don't need to report as many individual measurements, and also keeps the measurement data a bit more manageable. But so to test our EP-ping tool here, we performed a small 1 month long measurement study in a small ISP in El Paso, Texas, where we deployed EP-ping inside of their network. So right below the edge router, they have a little middle box there that all traffic passes through that runs this LibreQS system that they presented. And on this middle box, then we also deployed EP-ping, as this then allowed us to monitor the traffic for all subscribers. And from this vantage point, we essentially get two types of latency measurements. We get the internal leg between this point in the ISP core network and to the subscribers and hosts. So not just to their routers, but to whatever device they're actually connecting to the internet with, be it a phone or a laptop or an iPad or something. And then on the left-hand side here, we get the external network latency between the ISP and whatever upstream destination that the subscribers are actually connecting to. So to assess the overhead that our monitoring setup had on this middle box, We performed a simple A/B test where we simply ran for 1 week without EPPing to get a baseline, and then 1 week with EPPing. And then we compared the CPU utilization on the system. And after accounting for some slight differences in traffic load, we found that there was virtually no difference between these two periods. So to sort of isolate the overhead of EPPing more specifically, we also looked and measured the runtime of these eBPF programs that EPPing uses. And we found that they added up around 300 nanoseconds of processing time per packet. So this then translates to about 0.65% CPU utilization at the 130,000 packets per second or so that this ISP was typically handling. And if the traffic would scale up to 1 million packets per second, then we could expect around 5% CPU utilization for the monitoring part. Now, moving on to the actual RTT measurements themselves, on the left-hand side here, we have the internal network latency. And here we can see that it has sort of a gamma-like distribution with a peak around 14 milliseconds and then tapering off into a fairly long tail. That's quite typical of latency distributions. Whereas on the right-hand side here, we instead have the external network latency, where we instead see a much more multimodal distribution as the traffic goes to a few different data centers. So the big peak, for example, at around 18 milliseconds there is the time to the closest big data center in Dallas. And we also have much less of a latency tail on the external network part. Now, these measurements are not that surprising in and of themselves, but it's still interesting to note that despite this ISP operator using LibriQS with its state-of-the-art traffic engineering principles to sort of minimize unnecessary latency, we can still note that a fairly significant part of the overall end-to-end latency can still be found on the internal network part or leg, and especially when we consider tail latency. And this is largely down to the Wi-Fi connections that subscribers use inside their premises. We also looked a little bit at how the latency varied over time on the internal network. And to sort of try to summarize what this figure tries to show is basically that we found that network latency did vary over time, especially the tail latency. And we also found that it was partially correlated with the traffic load. So both latency and traffic load would increase during sort of the afternoon and then drop down in the evening and the night. Another aspect that we looked at was the latency towards some of the most popular autonomous systems. So in this figure here, the blue bars shows the fraction of traffic being served from these autonomous systems. And then the box plots next to the bars try to show the latency distribution towards that autonomous system. And here we can note a few things. One is, of course, that most of the traffic comes from just a handful of autonomous systems. And if we look at this, specifically the 4 most popular autonomous systems here, we can see that all of them have fairly low and consistently low latency to the point where the box part of the box plot is barely visible. But as we move to the slightly less popular autonomous systems, we start to see slightly larger variations in the latency. And this is largely due to the latency turning into a more multimodal distribution. But in all of these cases, we also can note that there is, of course, always a little bit of a latency tail. So just as 2 examples, this is how the latency towards Google looked like. We have this very sort of narrow peak around 18 milliseconds. Whereas on the other hand, for Amazon, we have a small fraction of the traffic being handled at that 18 millisecond peak, but then most of it goes further away, and we get this more multimodal distribution. So obviously, the stats for these particular autonomous systems are specific to this one ISP we measured from. But in general, we think that passively monitoring network latency in this way can help ISPs sort of figure out how well connected they are, and perhaps help with, for example, peering decisions. But to round this presentation up a little bit, so basically what we did with this work was that we demonstrated that it is feasible to, with just software, passively monitor the network latency for all subscriber traffic in an ISP. And with EPPing specifically, we were able to do that with fairly low CPU overhead while still collecting thousands of RTD measurements every second. That gave very detailed latency statistics about both the network latency inside the ISP network and outside. And from these latency statistics, one thing that we can note is that the last mile, or perhaps even more so the last few meters of access, remains a significant source of overall network latency. And this is to some degree not a very big surprise, even when you use active queue management and fair queuing. Tokia wrote a really nice paper on this, The Good, the Bad, and the Wi-Fi, showing this in testbeds quite a few years ago. But here we can note that this is still very much also a problem in real networks and something we need to be aware of. I also want to point out a couple of notable limitations that can be good to be aware of. One is that EPPing here works mainly with TCP traffic. So we don't get any latency for example, UDP or quick traffic. And that is, of course, a bit unfortunate, especially considering how those become more and more common, especially for latency-sensitive applications. So how to deal with that is still a bit of an open question. Another thing to note is that this was a pretty small measurement study, so it's a bit unclear exactly how general these results are. But we do plan on making sort of a larger scale measurement study together with LibreQS, where we look at the latency from more ISPs and also how it evolves for a longer time. Finally, I just want to mention that the EPPing tool itself is open source, so if you want to try that, then please go ahead. And the data set from this measurement study is also open source. And the last little thing is that, so parts of the EPPing tool has been integrated into LibreQS. So if you want to not only monitor latency, but also manage it, then I think LibreQS is a great alternative or a great solution. And they also have a very nice built-in dashboard that visualizes latency in a number of different ways. For example, this RTT heat map that can then help operators to very quickly find both when and where they have latency problems in their network. So thank you for your time. And if there are questions and time for that, I'll try to answer them.
Thank you very much, Simon. Very interesting stuff. I love to see some proper data. It's really cool. There's a question from Joachim here. Ryzen 5 3600 is much power compared to what is available on providers' gateways. Would it be possible to implement EP ping with eBPF on such SoC systems?
Yes, I mean, it depends a little bit on how much traffic you expect to handle. I will admit that we haven't done too many measurements on very sort of low power devices to see what the overhead would be there. But it should certainly be a lot faster than sort of doing traditional packet capturing. But unfortunately, I can't give a great answer there because I don't know exactly what the performance overheads would look like there.
Right. And I think you answered, there was one more question, but I think you already answered it. It was about whether or not the EP ping stuff is open source, and it is.
Yep.
All right.
And so is, of course, LibreQS also. So
yes. Okay. With that, we are done with the presentations for today. I want to thank everyone for attending, and I want to thank all the speakers for taking the time to come here and share their knowledge with us. That is really cool, and we really appreciate it. We have one more day of the event. So this is the agenda for tomorrow. We'll be learning about the Cloud Network Experience Index from Shezong Geng from Huawei. And then Dr. Madhan Raj Kanagarathinam from Samsung Research will talk about enhancing the real-time traffic latency in Wi-Fi networks from the smartphone perspective. Then Dean will talk about something. This slide does not include the title, and I unfortunately do not remember what it is. So that's a surprise. Then Mayur Chanagauda will talk about refining latency testing using application outcomes to measure impact in lab environments. Then James Carroll from Ookla will talk about internet observability at a global scale. And finally, Cohen de Schepper from Nokia Bell Labs will talk about L4S on Wi-Fi. So that's what we have tomorrow on the final day. And just a reminder as well, all of the presentations have been recorded and will be put on YouTube. And you, because you have signed up for this event, you will receive an email with those links as soon as they are available. So I hope to see everyone tomorrow, and thanks for attending the event today.